Hello, everyone. My name is Mihai Budiu. I'm a researcher at VMware Research and the co-chair of the P4 Language Design Working Group. And I have the pleasure to introduce the next presentation. This will be given by Cristian Dumitrescu, who is a software architect at Intel, and he's been a long-time contributor to the DPDK project. And he will give us the latest updates on the evolution to marry P4 and DPDK.
Okay, thanks very much, Mihai. Hi, folks. It's great to be here this year as well to present again to the P4 workshop. Today, we'll talk about how to develop your CPU network stack in P4. I just want to give folks an update on the new features that we implemented in P4 DPDK. Of course, first we will just reiterate what P4 DPDK is and what it is not, and then we'll look at some example use cases that we enabled lately, and we'll draw to some conclusions, and then look for questions. So let me start by showing you this picture about IPDK, which stands for Infrastructure Programmer Development Kit. It is an open source framework that is target agnostic, is community driven, is hosted on ipdk.io, and is basically an infrastructure framework that runs on many targets like IPUs, DPUs, switches, CPUs. And P4 DPDK is right in the center of that. It's right here, is the IPDK P4 based CPU target, alongside with another software target, which is P4 eBPF. P4 DPDK is basically a software framework, an open source software framework that allows folks to run P4 programs on multi-core CPUs. The goal is to develop better and faster software switches and as well as network stacks by combining the flexibility of the P4 language with the performance of DPDK. As I was mentioning already, P4 DPDK is used as the CPU target by the IPDK project, and it's an open source project that combines a compiler backend, the P4C compiler backend, from p4.org GitHub, along with some TDI repos. TDI stands for table-driven interface, on the same GitHub place, with a DPDK-based data plane engine that is hosted on dpdk.org. So hopefully you'll agree with me that P4 DPDK is getting better, faster, and more pervasive every year. Just a list of the various GitHub repositories that are all open source that people might want to take a look at, including the DPDK one, including the P4C one, TDI, and the P4 runtime server repos. What P4 DPDK is not, what I'd like to stress here is that P4 DPDK is not a simulator, it's not a P4 language simulator like BMV2 is. Performance is very important, is actually a key metric for P4 DPDK. It's measured in many millions of packets per second per CPU core, which is obviously scaled up and down depending on how many CPU cores you use and what kind of CPU, what CPU model you have. Just going to provide an update here on the features that P4 DPDK supports, the ones that we worked on and implemented since the P4 workshop from last year. So the ones in gray are the ones that we had last year. The ones in blue are the new ones that we implemented since last year. So last year, I think we had many I/O ports and many table types. We did implement new table types this year, like the LPM longest prefix match table type, match type. Basically, now you can use tables that have keys that have, as part of their keys, they have fields that could be exact match or ternary match or LPM match. We also implemented the action selector, which is a special kind of table that is specified in the PSA portable switch architecture specification. I'll have a slide on one of the use cases that mentions how this is useful. We implemented add-on miss tables with the timeout support. It's basically a special table type that is described in detail in the PNA portable network architecture specification. And that this table allows the data plane to manage itself, add entries to the tables. Traditionally, the P4 model, as folks know, is that tables are read-only for the data plane. In this case, for connection tracking and other use cases like learning, the data plane can decide in a programmatical way to add keys to the table itself. We had implemented support for var-bit headers, for packet mirroring and recirculation, for P4 runtime support based on the TDI, a table-driven interface, which is also hosted on p4.org GitHub. And also a lot of work on supporting the PNA architecture, and a lot of work to support more performance by using this compiled pipeline mode that I'm gonna talk in a few minutes on the next slide. I think, yeah, this is a new key feature that allows for much better performance of the pipeline implementation. And the way it's done is by simply, instead of using this specification file and working in the interpreted mode, where we simply execute instructions by executing a function pointer for each of these instructions that we have in that program. In this case, now we actually generate a C file with C code that contains all the code that the pipeline that is related to this pipeline. And now the C compiler will build this program, will have visibility of the entire code for the program, and can do a much better job at optimizing the program. We are creating a shared object library that is loaded by the target agent, as opposed to loading this text file, which is called the spec file. So just to get a few more details here, basically in interpreted mode, we are simply loading this specification file, pipeline.spec. This is a plain text file. What it does, what it contains, it's actually very similar to the P4 program. It is produced by the P4 compiler. There is a lot of work that compiler does by inlining, for example, control blocks that might be imbricated, or handling enumerations, or a lot of the front-end stuff that the compiler does. But at the end, what we get in this spec file is the definitions of the P4 objects in the P4 program, like headers, metadata, actions, tables. And we also get subroutines, one subroutine, basically one function, if you want, for every action and for every apply block of a control block. And these subroutines basically are built using instructions from a predefined ISA instruction set. We tend to call it sometimes a P4 virtual machine ISA, right? Because these instructions are high level. They don't work with like machine registers, like general purpose registers. They don't work with the memory addresses. They simply work with P4 objects. For example, we have an instruction to extract headers or emit headers. The operands are simply the header that we need to extract, or the header that we need to emit. Or we do look up into tables. The operand is the table itself. Now, there is a problem with this interpreted mode in terms of performance, which is that it is kind of slow, because as I was saying, for every instruction that we have there in the program, we tend to call a function pointer. We have to call a function pointer for each of those instructions. And then a GCC or CLang or any other C compiler is only actually seeing those small functions, which are the instructions themselves that are predefined, and it's not able to actually go across the pipeline and optimize everything together. Now, in the compiled mode, as I was mentioning already, we take this specification file and we generate a C file, and then we build this C file into a shared object library that we load and execute. So the difference is that now at this point, what we do is for every action from your P4 program, and for every apply block of a control block, we generate a single C function. And that C function obviously is still related to those instructions that we had in the spec file. We simply, for every instruction, we simply inline the associated C function of that instruction. So what we do, what we get in the end is a program that has all the code for the pipeline. It has one function for each action. It has one function for the apply block, which is like the main program. If you want an analogy with the C language, is the main function in the C program, and all these actions could be looked at as some kind of subroutines that get triggered by the table operator. The table lookup could be looked at as an operator. And now the C compiler can see all the code of the program. It will build everything together, and it will apply all the optimizations, and it will do miracles here. Really, what we see is typically a 30 to 70% performance improvement, depending obviously on the program itself. But for various internal programs that we have, this is what we get. So I definitely encourage people to use the compiled pipeline mode to get even more performance. Now, a good question is how to actually enable this pipeline mode. It's actually very simple. You don't need to do anything at the build time. Just when you run the target agent, you need to export this environment variable over here. It's called RT install dir. You need to set it to the path of your DPDK folder where we have the source code there, the source code that you used to build your DPDK application. So this is how we do stuff. We might want to change a few things, and maybe let me take a minute to explain why. So currently, the external controller over here will load the specification file, and it will load it on the target agent. It will send it and load it on the target agent. So it's the job of the target agent over here that runs on your data plane node to generate this C file. It's kind of very similar to just-in-time compilation, right? That eBPF, for example, uses. And also build this shared object library. So all this happens under the hood here silently on the target agent when the target agent is loading the specification file to the target and is creating all the pipeline data structures. Now, what could happen is that the compilation could fail here because, for example, you might not have a C compiler. The other thing that is not nice is that you are not really able to tune this build process. You might want to send some specific flags to the build process to customize a bit the build process. You cannot do that because it's kind of the options and the way to build this shared object is hard coded here in the library, in the pipeline library that is used by the target agent. So going forward, we want to do a few changes here. We want to basically take out this build process of the library and take it out from the library. Sorry, let me go back. Take out this build process of the shared object pipeline library that is associated to your P4 program, and take out this build process from the target agent and move it outside. Create a tool that will take the specification file, generate the C file, and also build it, right, by calling the C compiler. So whenever we'll be having these code changes, the external controller will be able to load this this shared object library instead of the specification file, and the target agent won't have to do any build anymore, and the performance will be much better because of the work that the C compiler was able to do. So stay tuned, and we hope to deliver that very soon. Now I do have 2-3 slides on the use cases that we enabled, that got enabled by these features that we worked on. We did a lot of work in the last year. So one of them is this VXLAN encapsulation example. Over here, the input packet is a plain Ethernet IPv4. The output packet is a VXLAN tunnel that has some other headers in front of the input datagram. It has an outer Ethernet IPv4 UDP and VXLAN set of headers. We tested this with 64,000 tunnels. That number can be increased to 1 million as well. The action here is actually quite complex. When a packet hits this tunnel table, if it matches the tunnel, what we do is we have to read all these outer headers, which is 50 bytes of packet headers from the table entry that was hit, and push them in front of the input packet. And we also need to update some fields that we are not able to pre-compute because they depend on the input packet, like the IPv4 total length and the UDP length in the outer headers. And we also need to update the IPv4 checksum of the outer IPv4 header. So these things are done as part of this action. It is like a 10 instruction action. We have to push these headers, and we have to do these updates. We do that by using about 10 instructions in the specification file. And by using the pipeline mode, basically, we will have a single function for the action, a single C function, as opposed to calling 10 function pointers to do this action. And because of this, we get 70% performance improvement for this use case. Another one is a P4 program that uses a complex FIB, a complex routing table, with VRF, virtual routing and forwarding support, and ECMP or weighted CMP support. And this is using this object, this P4 object called PSA action selector, is specified in the PSA specification. It's very good to implement, as the name says, ECMP routing. What happens is really when the packet hits a route in the routing table, instead of having a single next hop that could be used for the packet to get out, now we associate a group of next hops for the packet. We basically say we are good to pick any of the next hops from this group, as long as for a given for the same n tuple, for the same flow, we will always pick the same next hop from this group. So basically, there is some hashing done, a scheme that allows the affinity of a flow to a next hop, but different flows, different n tuples could pick different next hops from this table. So this is very good for load balancing as well, for example. And then your next hop table will do the action associated with just that specific next hop that was picked up. This action could be, for example, to send the packet to a specific output port, or put the Ethernet header in front of the packet, change the Ethernet header, or simply do anything else that it could specify in P4. So this got enabled by us supporting this action selector construct, which is quite complex but very useful. Now, on another use case that we want to mention, the connection tracking use case that uses the PNA add-on miss table. It is specified in this object. The add-on miss table is introduced by the PNA architecture. PNA stands for portable network architecture, network interface, network card architecture. Is basically one of the architectures on p4.org that discusses how to program a network interface card using P4. What happens here is that for connection tracking, for example, typically or traditionally in the past, the way we used to do it is simply whenever we discovered a new flow, we sent a message, or we sent that the packet itself to the control plane. So basically, we had a miss in the table, in the connection table. and we simply sent that packet or a message for that packet to the control plane, and then control plane had to close the loop and decide whether it wants to add, typically does want to add a new flow, a new key in this connection table. Now the problem with that is that this loopback through the control plane is very long, has a big latency, and some of the connections could be short-lived, so it might take longer to update this table than to basically do the data transfer through that connection and close the connection. So then it's very necessary for this use case to have the data plane, enable the data plane to add keys to the tables itself, not rely on the control plane to do that. So that's what's going on here. The default action is basically doing some conditional logic maybe, and on some of the paths from that code, you decide to add a new key to the table. The key that is added is exactly the current key that got missed into the table, right? And then later on, more packets will hit that, will hopefully hit that same flow. And now the regular action basically needs to decide what to do with that entry. Each entry has a timer associated with it. That's the way these entries are purged, are removed from the table simply on timeout. If these entries, if these keys are not hit, then eventually they will be expiring naturally. But then sometimes, and most of the times, basically, or on the real connections, you will get more packets for the same connection, and those packets will hit that key, and then you can decide to either rearm the timer for that that key. That has to be done explicitly. You have to call an extern in the P4 program in your table action to say, hey, please rearm the timer for this key. You could also decide to do nothing, and in this case, the timer will continue to run, and eventually that key will get expired unless there are more hits later on, and you might decide at that point to rearm that the timer for that entry. So it's very useful, for example, for TCP state machines for the connection tracking use case. So that's what we also enabled in our P4DPDK project. So just to jump to some quick conclusions, I think what we showed is that we did a lot of work lately in P4DPDK to enable more features, more performance, more use cases. Now P4DPDK is coming at that stage where people could use it to quickly develop complex network stacks running on the CPU. One example of this complex stack is the P4OVS project. It is an OVS fork that is under IPDK. Yeah, P4DPDK, I think we are becoming faster, better, and more pervasive every year, and hopefully more users will join to our community.
Thank you. This is really interesting. A couple of questions came to my mind during your presentation.
Yeah.
The first one is you show how much faster you are compared to interpreted mode, but you don't say if there is a gap between this and handwritten DPDK, and how much the gap is, and whether you hope to close it.
Yeah, that's a question that I often get from people, but the problem is that closing on providing an answer is not that simple, because to do that we simply need to get some volunteers that will offer their DPDK applications that should be complex enough, right? Will give us the numbers for those, and will just also provide the source code or a description to allow us to write the P4 program, or maybe they will write the equivalent P4 program. So in the absence of that, it's very difficult for us to simply just go and take a complex P4 program. It will actually be a lot of effort to take, for example, this action selector or any of the use cases that I presented, and just write it from scratch in DPDK. It will take many weeks, even probably more than that, right?
I was thinking even a micro benchmark. It doesn't have to be a complex application.
For micro benchmarks, I guess I guess it depends on what you're doing. If you do more like packet IO type of workloads, then if you just get the packet in and you send it out without doing much work on the packet, a handcrafted DPDK application will definitely be faster. But then the thing is, as you go into implementation stage, you will realize that, okay, there is a lot of code a lot of work to implement the data plane, but there is even more work to implement the control plane. So just having a way to update these tables while the data plane is crunching packets, avoiding stopping the data plane, and not losing packets, not getting congestion, not getting the queues full. That's actually a lot of work, and that's why we implemented this framework, because I don't want to go through the pain of writing an application from scratch again, right? I think I'd like to describe it in a very neatly and short and crisp amount of code in P4, and then I just want this code the C code to get generated from that, and that code should handle my tables, my table updates, and my table implementation, whether it's wildcard or LPM or exact match. I don't want to start all over from scratch, right? I mean,
this brings, yeah.
Yeah, I think if you want the ultimate performance, you might decide if you just have to write, if you are in a place where you only have one application to write and maintain, then I don't want to spoil your pleasure. Yeah, just go ahead and handcraft that application, but don't be disappointed if we can do it in a shorter amount of time, much shorter, in, let's say, hours or days, by writing it in P4 and getting the same or even better performance, right? But we do need, I agree, I agree, we need more data. Yeah. We need more data on this to show. We need more numbers, solid numbers to show it. Yeah.
That brings me to the other question, which is, do you have any idea how much easier it is now to write in P4? Have you done any studies like taking an application handwritten in DPDK and seeing how much simpler it is?
Yeah, so there are other open source projects that like, for example, open source network stacks, right? And some of them are even built as a tree of nodes. And what happens is that you pretty much have the same code or very similar code in every node, right? And in every node you find the same tables, whether hash or LPM or wildcard, that you need to build and you need to instantiate and you need to populate and you need to create your APIs to handle those tables, to update those tables. So I guess it's much easier to program those tables through P4 runtime. It's a solid API that simply works. It's the same API for any type of table. You just specify the fields that make up the key, the actions that you have to execute. So you get a lot of stuff for free. You don't have to do it over and over and over. You don't have to say, okay, this table is actually a routing table. It needs to be programmed this way. You need to provide these fields. You need to know about IPv4. And
I see.
This sort of stuff. Everything is more generic. So I think you get a lot of things for free by using P4. And it is, I mean, the biggest P4 programs that I was able to see is less than 5,000 lines of code, right? And I've been able to see C projects or RTL projects with millions of lines of code. So there is a big difference.
It sounds big. This brings me to my final question about this table-driven interface. Is that an alternative to P4 runtime?
No, that's a great question, Mihai. So table-driven interface is just, I think, the local API that needs to run on that we are proposing to as a standard to run on the target agent. And that's the API that the gRPC protocol, the network passing, the message passing protocol of gRPC that goes through the network under P4 runtime connects to, right? So basically those calls from the remote side of the external controller to the target agent, they go through the network, we send packets, but we just feel the need also to standardize the local API that is called by those P4 runtime messages. So that's what TDI is. It's very generic. It's pretty much the local API for P4 runtime. That's what it is. It's not a different. It's not an alternative to P4 runtime. We actually have a P4 runtime server that is built on top of TDI, or we are working to make that happen.
I see.
And the repository is on this slide. We have this. Is it the Stratum repository? I think that there is a work in progress there to port the P4 runtime to make it work on top of TDI interface as one of the possibilities.
Thank you.
Thank you.